In this section we're going to be looking at kinematics, which is essentially looking at particular motion, and hopefully we're going to be able to put some of the techniques and concepts that we've learned about so far into a kind of more useful real-world context. So to start off with, we're going to have a look at the difference between displacement and total distance travelled and how we can interpret that in the context of integration. So consider that we have a function here. So S stands for displacement. So this is the displacement function here, t squared minus 4t plus 3. If we find the derivative of this, we should remember from earlier work on differentiation that the derivative of the displacement function will give you the velocity function. So if we find the derivative of this, we end up with 2t minus 4. So this is our velocity function here. We know that speed equals distance over time, so if we've got a graph with, well, in this case, velocity, that would be displacement over time. So we can find the displacement by calculating these individual areas, A1 and A2, and adding them together. However, because we are looking at velocity and displacement as opposed to distance and speed, displacement is a vector quantity. So it means it has direction as well as magnitude. So we have to take into account the sign. So when we calculate the displacement, if we rearrange the formula, so if we have velocity equals displacement over time, then we can say displacement equals velocity times time, or in the context of this graph, the area under the graph. So A2 is no problem, we can just do half times base times the height to get the area of A2. However, for A1, if we do half times the base times the height, we've actually got a negative height here. So this is going to give us a negative area. So the displacement is actually going to give us, if we were to work it out geometrically, negative 4 plus 9, which is going to give us 5. We can calculate the total displacement by just calculating the integral between 0 and 5 of the velocity function. We are not working out the absolute value of the area here. We are working out the displacement. So we can see that just by substituting these values in, we're going to automatically get an answer of 5. So if you did this on your calculator, your calculator is going to work this out for you, but what it is doing is taking this positive area and adding it to this negative area here to get this solution here. If you wanted the total area under the line, you're going to see this is going to be problematic because we're actually getting a small answer. So the total area under the function here between the x-axis is actually going to give us the distance. And in order to find the distance, we're going to have to do something different. We're going to have to take the modulus of the velocity function. So this is, if this is our velocity function 2t minus 4, this is the modulus of the velocity function. And in doing that, we can see that not only is A2 positive, but A1 is also positive. So the area under a velocity time graph would actually give us the total distance, because here distance is a scalar quantity. We're only interested in the magnitude, so we're not interested in the sign. So we're going to take the absolute value and add these two together, and that will give us a total distance of 13 in this context. So taking that on board, we can say that to generalize, the total distance between t1 and t2, if we integrate, the modulus of the velocity function with respect to time is one way in which it can be found. So let's have a look at a question here. Suppose the displacement function for a particle moving along a horizontal line is given by s of t, the displacement, equals t squared minus 4t plus 3 for values of t greater than or equal to 0, where t is measured in seconds and s is measured in meters. So the first part of this should be hopefully a bit of a review, and then questions 4 and 5 give you a chance to draw on what we've just looked at. So first of all then, find the initial displacement, the displacement after 2 seconds, find the velocity function and use it to find when the particle changed direction, find the change in displacement after 5 seconds, and how far the particle has travelled after 5 seconds. So have a go at that, and then I'll go through that with you. So part 1, the initial displacement. So for that, our time, whenever we see initial, that means time equals 0. So we're just going to substitute in 0 and find f of 0, and that's going to give us 3. Similarly, the displacement after 2 seconds, we're going to substitute in and find s of 2, which gives us -1, or 1 unit to the left of the origin. And similarly here, this is 3 units to the right of the origin. We can represent that on a diagram here. So if this is our origin, when we start, we're here, 3 units to the right, and after 2 seconds, we are 1 unit to the left of the origin. So we can mark those on with that motion diagram there. How can we check this using integration? Well, hopefully you can see that in this instance, we are looking at the displacement, and we know that displacement can be found by integrating the velocity function, because we know that the antiderivative of velocity is displacement. If we integrate the velocity function between 2 and 0, that would be the same as taking the substituting in for values of s of 2 and s equals 0, which we've already got our values in the first 2 parts of the question. So we can check that that's -4 as well. So it tells us that at 2 seconds the particle is 4 meters to the left of where it was at 0 seconds. This then is the general formula here for the change in displacement from time 1 to time 2. Part 3, find the velocity function, use it to find when the particle changed direction. Well, for this, the velocity function, we're just going to find the derivative of this, which gives us 2t minus 4. We're going to set that equal to 0 and solve for t, and we can see that t is going to equal 2. So we know that at t equals 2, the particle is going to change direction. So, and we can check that because, for instance, if we substitute in a value of a t less than 2, so if we substitute in 1, that's going to give us a value, a negative value, which means it's moving to the left, and we can substitute in a positive value. So for instance, if we substitute in 3, that's going to give us a positive value, which means it's moving to the right. The displacement after 5 seconds then. So here we can use what we looked at the start of the video, where we just find the integral of the velocity function between 5 and 0, and on our calculator, or working it out by hand, we can find the answer is 5. So after 5 seconds, we know that it is 5 units to the right of where it started, because displacement is, we're looking at the change in position. So if it started, t equals 0, here, 3 units to the right of the origin, 5 seconds later, it's 5 units to the right, which is going to be up here at 8 units to the right of the origin. How far has the particle travelled after 5 seconds? This is when we're going to use the modulus function. You can see intuitively that we've charted this whole motion, this whole journey now, so you can see intuitively that it's 13. If on our calculator we substitute that in, so we're actually going to find the absolute value of the velocity function, so 2t minus 4, between 5 and 0, and that will also give you the same answer. Right, here is another question for you to have a go at. The displacement function for a particle moving along a horizontal line is given by a displacement function equal to 8 plus 2t minus t squared for values of t greater than or equal to 0, where t is measured in seconds and s is measured in meters. So find the velocity of the particle at time t, find when the particle is moving right and when it's moving left, draw a motion diagram for the particle like we've just seen, and then this last part here, question D, write definite integrals to find the particle's change in displacement and the total distance travelled on the interval of t between 0 and 4 inclusive, using your GDC to evaluate these and checking them on a motion diagram. So have a go at this and then I'll go through that with you. Part 1, find the velocity. We've looked at this already, it's the first derivative. Part B, find when the particle is moving right and left. So again, set this equal to 0 and solve for t equals 1 second. So we can see that for values less than 1, so if we substitute in 0, it's going to be positive. So we know that for values between 0 and 1 inclusive, it's up until 1, it's going to be positive, so moving right. If we choose a value greater than 1, so for instance 2, we can see it's going to be negative and moving to the left. So for values of t is greater than 1, it's going to be moving left. Draw a motion diagram for the particle. So we know that initially, at time t equals 0, it is 8 units to the right of the origin. We know it changes direction at t equals 1 second, so let's find the point there. So when after 1 second, it is 9 meters to the right of the origin, and we can then put that on the motion diagram. So we started here at time equals 0, 8 units to the right of the origin, 1 second later we're here, and we know it then changes direction. Part D, write the definite integrals to find the particle's change in displacement and the total distance travelled on the interval between 0 and 4 inclusive. So first of all then we want to find the change in displacement, which is just the integral of the velocity function between t2 and t1. So we've got the velocity function, we can integrate that, and we can find the total change in displacement is negative 8 meters. Remember, it's displacement, that's why we've got the sign there. So the finishing position at time for t equals 4 seconds is 8 meters to the left of the origin. For the distance, remember we need to take the absolute value, or the modulus of the velocity function between t1 and t2. So again, on your GDC, you can substitute that in and you will end up with a value of 10 meters in total. It says confirm your results on a motion diagram, which we can do here. So we started at a position here, 8 meters to the right of the origin. 1 second later, we were here, so we've travelled 1 meter. And then at t equals 4, we are at a displacement of 0. So the total distance then is going to be that 9 plus the 1 which we've got here. And the total displacement, if we started at 8 and ended up here, it's 8 meters to the left, which checks out. We can have a look here again at this idea of representing the displacement and distance on a graph. We've got the velocity function v in meters per second of a particle moving along a line. Find the particle's change in displacement and the total distance on the interval between 0 and 16. So fairly straightforward this. For the total displacement, you could either integrate it, the whole thing, or just find out each individual area geometrically and add them together. For the total distance travelled, you are going to have to either take them, but we don't actually have the function here, so we can't integrate. For this, you are going to need to find out each individual area and take the modulus of each area and add them together. So for the displacement in that instance, we said, sorry, we can't integrate. We're going to have to find the individual areas and add them together, recognizing that this would be negative. So again, we don't know what this function is, so we can't actually integrate it on our calculator, but we can work it out by calculating each individual area. As I said, recognizing these two are negative, and that will give us 3 meters. For the distance, we could take the modulus, reflect it here, or you could just, going back to here, you could just take the positive value of A1 and A3, take the absolute value, and if you add those all together, you would in effect be calculating the modulus, the integral of the modulus between 0 and 16, which would give us an answer of 29 meters.